Hi, I'm David Turner, and I love programming. Recently, I was hacking on Git, and I wanted to sort a list of paths. There was a constraint. The paths had to be sorted topologically, so that foo comes before foo/bar, comes before foo/bar/baz, and nothing comes in between foo and the first file inside foo. ASCII order doesn't quite achieve this, because dash comes before slash, so foo-flee would come after foo, but before foo/bar. This is relatively straightforward to solve. We just reorder the alphabet a bit so that slash is second, immediately after 0, which is used to indicate end of string. And everything from 1 up to slash, which is 47, would move up 1 to make room. So we can do it with a couple of if-else statements. We could also use a lookup table, which is slightly faster, but it still wasn't fast enough. The comparisons were a hotspot in my code. So what I actually decided to do was change the code entirely so I didn't need to sort. But what I considered first was to use the single instruction, multiple data instructions that are available on modern processors. This is the crazy fun way to make code fast. So processors store data that they're working on in registers. These are basically your processor's version of variables. And ordinarily one variable holds one value. On a 64-bit processor, that's a single 64-bit value. But with SIMD instructions, a register can be treated as an array of independent values. And Intel's implementation of SIMD is called SSE. So for example, you could treat 128 bits as 4 32-bit integers, or as 8 16-bit words, or as 16 8-bit bytes. And the nice thing about this is that each value in a SIMD register stays independent, so that if, for instance, you're adding 2 arrays of bytes, and one of the bytes overflows, it doesn't carry into its neighbor. So I can process 16 bytes of my string at a time. Because strings are a little bit complicated, let's start by walking through an example of SIMD with pixels. So imagine we have an image which has 32-bit pixels. That's 8 bits each for red, green, and blue, and 8 bits of padding. So we want to lighten this image, so we'll add, say, 40 to each channel of each pixel. Here's the code to do that. Let's unpack that. So first we'll load 4 pixels into a register to work on them, right? And to read this, we'll start with move, which just means copy data. DQ means double quad word, 16 bytes, or 4 pixels. And A means align to a 16-byte boundary, which is faster, so we'll just make sure to arrange our image data that way. RDI is this ordinary 64-bit register, and by convention it's used to pass the first argument to a function. And the parentheses here mean to get data from that address, just like a pointer dereference in C. And XMM0 is the first of our 8 SSE registers. So we pass a pointer into this function, dereference it, and put the result into a register. Easy. We're also going to need the data that we're going to use to lighten. That's just going to be 40 12 times, like so. Let's say that our function takes a second argument, which points to this. And that's also nice because it'll later let us vary the effect. So we can do only the red channel, for instance, with 40 and the 4 red channels and 0 everywhere else. So we're going to add this lightning data right in, right? And again, this is a complicated chunk here, but to read it out, P for packed, add, U for unsigned, S for saturated, B for bytes. So saturated means that if we hit the top, right, 255, we don't wrap around to 0 again as we would ordinarily do. We just stay at 255. And that's what we want. If our pixel is already as bright as it can get, then lightening it won't do anything. And where before we had RDI, now we have RSI, which is the second argument to the function. And here's the result. You guys can actually see that up there, good. And of course, we need to put that pixel back into memory. And that's just the same as the first instruction with the operands swapped. So we've just transformed 4 pixels in 3 instructions. Not bad. But our string function is more complicated. It didn't just have addition, it also had an if statement. And so we're going to look at a simplified case here, which is just to replace all the slashes with 1s. So how does your processor do an if statement? You do a comparison, which sets some flags, and then you do a jump, a goto, that's conditional on those flags. But we can't do that with SIMD, because some of our comparisons might be true, while others are false. We can't both jump and not jump. Instead, we need to get the effective if-then-else, without any conditional jumps. So here's where we're going to need to do some bitwise arithmetic. And I'm going to show you this visually, because that's how I learned it. So the standard approach is to take a mask with 1s where the condition is true and 0s everywhere else. Here the 1s are white and the 0s are black. Recall that or giveth and taketh away. You and the then value with the mask. And with 0s gives you 0s. And with all 1s changes nothing. You and the else value with the inverse of the mask. And then you use OR to combine them. Notice that the operands to the OR each has black zeros where the other has color. We OR them to create a complete image. ORing anything with 0 just gives you that thing back. So think like a dovetail. So let's implement this piece of our string function this way. So we have some register containing 16 bytes of our string, and we want it to contain 1 only in the bytes where it previously contained a slash. Let's assume for now we have this register XMM7 that holds a slash repeated 16 times. And we'll want a register where each byte is 1, XMM6. And then a register where each bit, not byte, is 1, XMM5. And finally, we'll have our string in XMM0. So first, we're going to save off a copy of our string because we're going to clobber it. And we're going to do this byte-wise comparison between our register and the register with all the slashes. Right, so that's packed, compare, A for equality, B for bytes. Notice it's only got 2 arguments, the 2 things it's comparing. So where does the output go? Well, it clobbers the second argument, so it's a good thing we made a copy. And the output is one of those masks we wanted. Any byte where the 2 arguments are equal gets filled up with all 1s, and any byte where they differ gets filled up with all 0s. So we started with the string /2/power/ example, and our mask has 1s where the slashes were, and 0s everywhere else, which is good. And now we're going to copy that mask, again, because we're going to clobber it. And we'll build the part of the final value that contains the 1s. Remember that XMM6 contained the 1 bytes. So we use AND, right? And so now XMM2 has 1 bytes where the slashes were. And now we need to build the other part of the final value, so we need the opposite of that mask. And there's no SSE not instruction, so we have to use XOR with XMM5, our register full of 1s. XOR with 1 inverts, so that's what we want. And now we're going to AND that with our original string, which was in XMM0. And so now XMM0 has 0s where the slashes were. Right? And so you'll notice that XMM0 has 0s, holes, exactly where XMM2 has 1s, notches, let's say. And that's what we wanted, right? So we can use OR to put them right back together. And now we've reached our goal. The slashes were replaced by 1s. We only use 7 instructions to process 16 bytes. The one wrinkle in all this is that we're using C-style 0-terminated strings. So if we're comparing 2 strings, we need to know when either of them ends. And conveniently, Intel has given us an instruction that does precisely that. PCMPISTRI, so that's packed, compare, implicit, meaning 0-terminated, strings, returning index. There's also an explicit if you happen to know the length of your string. Basically, this is an instruction designed explicitly for the strcomp function. And it's got some bells and whistles, which let you use it for more advanced things, but we're going to focus on the strcomp case. So the idea is that we want to find out the index of the first difference, but only if that difference is before the first 0 in either string. And at the same time, we want to find out if either string has a 0 in it. Conveniently, PCMPISTRI does this all for us. It puts the index of the first real difference into the RCX register, just an ordinary register. By real here, I mean before a 0, so inside the actual strings. And then it sets some flags, the carry flags if there were any if there were any real differences, and the 0 and sign flags if there were any 0s in the arguments. In our case, any of those flags should be enough to get us into the routine which tells us which string is greater. And if none of them are set, we can just move on to the next 16-byte block of our string. So the difference routine is actually a little bit complicated. And that's because we have our values in these SSE registers, but we need to extract the single byte where the first difference is. We have the index of that byte, and it turns out that there's not an instruction that does that for us, gives us the byte given the index. So after some searching, my slide notation has gotten messed up. After some searching, I found a thread where the glibc folks figured out the simple way to do it, which is with the shuffle instruction. And unfortunately, I'm going to run out of time to show you that the details. But if you're interested, look up these slides online and keep watching past the credits. So this and/or thing and the shuffle trick are the sort of a weird creativity that Intel's wacky instruction set encourages. So it really is a perversely pleasurable way to program, because you end up with this tremendously efficient code, but you have to really fight for it. And you can actually get even deeper when you consider the timing of instructions. So what happens when one instruction depends on data computed by another instruction? And so maybe it has to wait. And in that gap while it's waiting, you can start processing the next chunk of pixels. And now you're interleaving the two computations, and you start to run out of registers. So you have to be clever about reusing registers. Thank you.